covered these reactions that sort of connect other metabolites to the citric acid cycle. This is the complex figure in the book, and these are the 4 reactions that are considered to be anachlorotic reactions. Let me show the table version. This is a little simpler. These are the 4 reactions. The 3 that I pointed out were the first 2 that we saw previously on gluconeogenesis, pyruvate carboxylase, carboxykinase. They're showing both of these reactions being reversible. In the cell, I'm not sure if pyruvate carboxylase ever goes left to right, but anytime it acts in metabolism, it seems like it goes from left to right instead of right to left. So that's the reaction that we saw before. This reaction is reversible in the cell, apparently. Again, we saw it going left to right. The third reaction is the one that I skipped because it's not found in mammals and humans. And so we're going to skip that one. And then the fourth one is this enzyme called Malic enzyme, which for some, this is sort of an important enzyme, I think, in some way. And again, this is sort of the anachlorotic direction, making malate, replenishing the citric acid cycle. But going in the opposite direction is also important, as a way of taking the citric acid cycle intermediate and taking it out of the citric acid cycle. There are other ways to do that, but I think this is one way that's important. So, those are the reactions we went over last time. I'm going to not say anything more about it. Instead, I want to move on to this glyoxide cycle. So, before we do the glyoxide cycle, let's remember what the citric acid cycle is. Citric acid cycle is you take acetyl-CoA, you combine it with oxaloacetate, it makes citrate. And then, if you go around the cycle, what happens? You regenerate the oxaloacetate, and you make 2 molecules of CO2. So, and as I said a number of times, what's the net reaction of the citric acid cycle? It's oxidation of the 2 carbons in the acetyl-CoA to make the CO2, right? And there's other NADH is a product, CoA is a product, et cetera, et cetera. But that's, you could say that's what the citric acid cycle does. So, in humans, we can make acetyl-CoA from pyruvate, from glucose. We can make acetyl-CoA from fatty acids. And then what can we do with the acetyl-CoA? We can combine it with oxaloacetate to make citrate, and we can either complete the citric acid cycle. We can take the citrate and use it to make fatty acids or cholesterol. To do that, we actually take the citrate and break it apart to make acetyl-CoA. So we can take acetyl-CoA, and it's not shown explicitly on this slide, but we can take the carbons in acetyl-CoA and use them to make fatty acids. Right, and then we can do the reverse. Other than that, there's not a lot we can do with acetyl-CoA. There's not a lot we can do with the carbon atoms in acetyl-CoA. All right, I want to describe the reactions of the glyoxylate cycle. Which is found only in plants and some bacteria. It's not found in humans. It's not found in other vertebrates, like rats, for example. This will be relevant later. All right, so why do I cover the glyoxide cycle? I'll try to make that clear in a few minutes. So what is the glyoxide cycle? The glyoxide cycle starts with acetyl-CoA. And the acetyl-CoA is combined with oxaloacetate by citrate synthase to make citrate. The citrate is then isomerized or rearranged to make isocitrate. The reaction catalyzed by a conitase. Right, so far, this is exactly the same as the citric acid cycle. Right? But the important thing is that these organisms have an enzyme that humans do not have, which can take isocitrate That's isocitrate. And can break the isocitrate into two pieces. The enzyme can break that carbon-carbon bond. And I'm not going to go through the mechanism, but the products from the isocitrate are these two carbons are released as this molecule, which is called glyoxylate. And the other four carbons, you have to protonate that carbon, you get succinate. Okay, so succinate, of course, which comes later in the citric acid cycle. Right? This enzyme is called isocitrate lyase. And it breaks apart isocitrate into these two products. Okay, so so far, if you add everything up, we've used an acetyl-CoA, we've used an OAA, and we've made a succinate, and we've made a glyoxylate, not glyoxylate, sorry. We've made a CoA, a few other things. Right? So what happens next? So what happens next is a second enzyme that humans also do not have, which is going to catalyze this reaction. Well, Emery's just showing the mechanism. It's a point that we've seen numerous times. Take a second molecule of acetyl-CoA, deprotonate it to make the carbanion the same carbanion nucleophile that we've seen a bunch of times. And now this can react with the aldehyde of the glyoxylate, and continue down here, you get that bioester, and the enzyme then continues the reaction. This is an intermediate. The enzyme catalyzes hydrolysis of that intermediate, and the product that you get, I'm going to write it the way we've written it before. Is that plus CoA. Anyone recognize that molecule? 4 carbons, no H here, carbon 2. It's in the citric acid cycle. This is malate. And the enzyme that catalyzes both steps, the one on the upper board there, and this as well, the enzyme is called malate synthase. Okay, so what's the net reaction? What's the overall reaction? If you add up all this stuff, well, we're not quite finished, right? So now we've used 2 acetyl-CoAs. This one up here, and then this second one down here. We used an oxaloacetate, we've made a succinate, and we've also made a malate. You could take one of these. The easiest thing is to say, let's take the malate, let's use it to regenerate the oxaloacetate that we used in the first step. Right, so let's take this malate and let's oxidize it using NAD. We'll oxidize the alcohol, we'll get oxaloacetate. This is malate dehydrogenase, which is the enzyme for the citric acid cycle. So by taking the malate that we made, we can regenerate the oxaloacetate that we used. So there's no net loss or gain of oxaloacetates. But what is there a net gain of? Succinate. Okay? So the overall sum of all this, if you write it all out as a series of reactions and then cancel stuff that's made in one step and use it, and use stuff in the next step, you can write that the overall reaction is 2 molecules of acetyl-CoA makes one molecule of succinate plus 2 CoAs. Right, so that accounts for the 4 carbons in the 2 acetyl groups. They're succinate. Now we had to use an NAD to regenerate the OAA, so we have to include that. So an NAD is used, and NADH is generated. And then there's some other stuff. I think there's 2 waters that get used. I think that's about it. There might be some proton. Well, I put a proton there. So that's about it. Yes.
So you're saying that now they dehydrogenase is what takes malate and turns into oxygen.
Right, and that's again, that's the cycle. So here's the cycle. Oh, here's the citric acid cycle that I should have reminded you all of. So citrate synthase, so I say malate dehydrogenase. And again, you put in 2 carbons and you lose 2 carbons. Right? Here's the glyoxylate cycle. Right? So start with an acetyl-CoA, oxaloacetate, make citrate, make isocitrate, but then isocitrate lyase and malate synthase. So isocitrate lyase gives you the succinate, and then malate synthase allows you to regenerate the malate, which is converted back to oxaloacetate. So it's another cycle, but now the product of the cycle, rather than being carbon dioxide, as I said, the product is succinate. So the significance of this cycle is that it's a biosynthetic pathway. It's a pathway by which the carbon atoms in the acetyl-CoA, rather than just being lost as CO2, they're retained. They're retained in the form of succinate. And so what can the cell do with the succinate? Well, one thing the cell could do with succinate, the plant, is it could convert it also to oxaloacetate. Right? So this would be succinate dehydrogenase, you get an FADH2. This would be fumarase, you use water. This would be malate dehydrogenase again, you would get an NADH. Right? This is OA, but this is a new OAA, right? The carbons in this oxaloacetate came from the 2 acetyl groups, right? So this is in addition to this oxaloacetate because we used this succinate, right? So we have net synthesis of oxaloacetate from acetyl-CoA. What could we do with the oxaloacetate? One thing the plant can do is make glucose. Right? So plants in their seeds have oils that are basically fatty acid or fat, but they have fatty acids, and they can break them down, and they can use it, probably maybe in a lot of ways, but one thing is that they can use it to make glucose. Right? But it's because of this pathway that provides a way to do something with the acetyl-CoA other than just making it into CO2. And it provides a way, again, for the net synthesis of succinate, therefore oxaloacetate, therefore glucose, all using the carbon atoms from this molecule. So that's kind of a nice thing to be able to do. As I said, humans can't do that. Okay? So that's about the glyoxylate. Yeah, so it's in plants and some bacteria, but not humans. Any questions? All right, so remember these points that I made. Because now I have a bunch of quick questions. Some of which are to illustrate some points, and some of which are just to remember all the reactions we can do. So these problems are not really mechanism problems all this time. These problems have to do with all these pathways we've been studying and how they connect. And how can you get from one starting point to an ending point? Right? And in at least one case, you can't get there. Well, that really only applies to one of the slides. All right, so it's the usual, yeah, it's 5 points. So I won't have to do much more today. So your response where it's Bchm 462, the Cooker channel is 44. I hope they're all going to work. All right, so each of these questions involves the following situation. This is sort of a common, not so common today, but the way that a lot of these metabolic pathways were worked out is you extract the liver from a rat or something else and you make an extract, right? So you break open the liver cells and all the cell contents will be released into a buffered solution. So you have an extract, a buffered solution that contains all the enzymes. So all the enzymes for all the pathways we discussed so far, they're all present in this extract. They're all active, they're able to catalyze their reaction if they find their substrate. Right now, other stuff like ATP, NAD, that's all there. Let's assume that. So none of the questions revolve around saying, oh, you need NAD and there isn't any. Yes, there is. Okay? So all those kind of stuff, CoA, NAD, phosphate, ATP, ADP. If you're not sure, you can ask. Right? Now, for the purposes of my questions, let's assume that the citric acid cycle intermediates they're there, but there's not a whole lot, right? There's enough, that the cycle could happen, but let's assume just a micromole or so, which for these questions is a small amount. Right, so the question is going to be, what happens if we now add stuff to this extract? What could be made? So that's basically just the question. I have a whole bunch of them. We're fine. So question number one. This is an easy one. All right, you take this extract. So again, here's the extract. You add oxaloacetate, 1 millimole of oxaloacetate to your extract. How many millimoles of glucose could you form?
How many glucose?
This is here's your possible answers. I said this is an easy one, of course. It helps if you remember some stuff that we did weeks ago. But if you don't, you look it up, let's discuss with your neighbor, come to a consensus, and then you can enter your answer.
Oxaloacetate. I knew there was, because if you go for OAA, you're doing gluconeogenesis, right?
But gluconeogenesis, don't they need? So it's usually go from pyruvate to oxaloacetate, right? And then is this reversible?
Yeah.
The pyruvate carboxylase mechanism?
I don't know it's reversible.
That's
It uses
what-
ATP, right?
That's what I'm saying, because I only have these. I don't even know. Can you even go back from oxaloacetate to pyruvate?
I don't think so. I think it's a set.
That's what I think it's zero. Didn't you just say that that's the great thing about plants, that they can take? I mean, it's so sweet. I know. Is there a way to get from oxaloacetate back to pyruvate?
That's what I was wondering.
There is, because you're using ATP.
Yeah, you said you can have it. You said you can have all these things. You can have it. But how do you know a way to get with ATP oxaloacetate into everything? Do you know how to do that?
It's just
Okay. Well, that's with that third animal.
yeah, it doesn't apply to animals, it's only plants.
So, that's why you said it's like.
You got 30 seconds.
I did. You should click. You click over it.
Yeah. I just put one pyruvate. Oh, I think maybe it's the same because
So what's the answer?
damn. When I just looked, you can. It's 2 times. Look here. There it is. 2 times oxaloacetate.
The correct answer is 0.5 because remember, oxaloacetate is preferred to E, which is 3 carbons. but we need 6 carbons to make a glucose. So 1 millimole of PP is enough to make 0.5 millimoles of fructose 1,6-bisphosphate, which is enough to make 0.5 millimoles of glucose. So it's 0.5. You can't get 1 because oxalate is only 4 carbons. Okay, very good. So that's the answer. Okay. Question number 2. You take a rat liver extract. Let me ask before I ask, is a rat a plant? Is it a bacterium? So this is a rat liver extract. It's got all this stuff in it, same stuff, right? You had 3 millimoles of acetyl-CoA in the extract. How much glucose? How many millimoles of glucose can you form?
These are like regenerating.
But this is just for plants. I think this one is the one what I thought it was. I wish I would have seen that. Oh, damn. It was standing right there. But you know, if you have acetyl-CoA, usually acetyl-CoA.
One of those is the best answer, I would say. Given this information and other information from earlier today, including stuff you need to start with.
I'm like
Like usually for all mammals, the only thing that mammals can do with acetyl-CoA is put it into citric acid cells.
Then OAA can
But then you could do it.
yeah, OAA can make glucose, right?
So yeah, you could do acetyl-CoA with oxaloacetate. Oh yeah, look. And then once you have the acetyl, you could Thank you. What do you? I'm going to repeat. Huh? Because you can do a little bit of this oxaloacetate and half of it.
Right. It should be something else. I'm definitely going to link to this. It helped me with the lesson.
To do what? Read the book?
I mean, certain chapters, like,
Yeah.
I used to be fascinated by this, but now I can't.
What's wrong?
I knew it.
Bats are not plants. Bats are not bacteria. The oxalate cycle is in plants and bacteria. It's not in humans. The oxalate cycle is a way to take acetyl-CoA and preserve the carbons. But rats and humans, we don't have this. So we can't preserve those carbons, at least not to the extent of getting them into oxaloacetate. So the citric acid cycle doesn't make oxaloacetate. You put in acetyl-CoA, it combines with an oxaloacetate. This is the citric acid cycle. There it is, right here. Right? You put in acetyl group, it combines with an oxaloacetate. You start around the cycle. Those carbons are CO2. All you do is regenerate the oxaloacetate that you started with. So there's no net production of oxaloacetate from acetyl-CoA. So you started with a little bit of OAA in there, so you could use that to make glucose, but that's it. Right? So no matter how much acetyl-CoA you have, you can't use it to make glucose. Humans can. Plants can. That never seemed fair to me. But the other point is that, so if you're like on a low carbohydrate diet, so your liver does whatever it can to make glucose, to maintain your blood glucose. But all the fat that you store, none of that does you any, well, the fatty acids don't do you any good. We can't make glucose from our stored fat. We can use it for energy. We can use the glycerol component of the fat to make glucose, but we can't use all those carbons in the fatty acids. And that's sort of going to be relevant, actually. We'll come to that fatty acid metabolism a little bit later. There is an alternative way. There's one other way we can use acetyl-CoA. That will come up much later, but we're not there yet. Okay, so this is sort of the reason I use this question. I mean, most of you got it, but a fair percentage. Well, I guess this A was sort of a B question. On an exam, I would get part of that. But it's kind of counterintuitive. But again, the idea that the citric acid cycle, there's no net production of anything that's in the cycle. Everything is made in one step, it's used by the other. So think about that at home if you need to. Let's move on. All right, so there's the answer. All right, so on the other hand, the reactions of the citric acid cycle are actually very useful for things other than doing the entire cycle. So now let's consider a second way to make glucose, which is, let's consider starting with an amino acid. I use glutamate. Right? So if you were eating a low-carbohydrate diet, your liver would make glucose from amino acids, assuming you had protein in your diet. And it turns out 18 of the 20 amino acids are glucogenic. 18 of the 20 can be used to make glucose. So the question is, if you remember the structure of glutamate, it's this. So this is 5 carbons. 5. So the question is, what sequence of reactions do you need to get from glutamate to glucose, right? So the first reaction is one we haven't done yet. So it's shown on a slide, and I think I mentioned it, but I'll just show it to you explicitly. The first reaction is this one. So that makes alpha-ketoglutarate. Right? So that makes it easy. So when we say we're going to start with glutamate, that's essentially the same as saying we're going to start with alpha-ketoglutarate. So let's say we add a bunch of glutamate or alpha-ketoglutarate to this extract. Now the question is, the answer is we can make glucose from these carbon atoms. And so the question is, what are the pathways and enzymes that are required? Right? So in my question, let's say we're going to add 2 millimoles of glutamate to this extract. And what are the pathways and enzymes required to make glucose from the glutamate via alpha-ketoglutarate? So this one is also relatively easy. On the second exam, I asked a question sort of like this, where we started with glucose and you had to use the pentose phosphate and glycolysis. So I'll give you these possible answers, but you're not going to have to tell me every step, but which pathways do you need to connect to? Okay, so let me. All right, so it's the same old story, same extract. So here's some possible answers. And again, if I say citric acid cycle, it could be the whole thing, or it could be part of it.
Oh, sweet. That's part of it. Sorry.
too.
There's one best answer, I would say. Use the answer that's most economical. And I don't want to get into arguments about whether other ones will.
Which one is
The fewest steps.
Which one is what does the malic enzyme do?
Which one?
The malic enzyme. I don't know.
Yeah, I'm not really clear about that.
So you actually said with alpha here, and then that's the citric acid side, right? And I think everything is reversible. Right?
Right, so
Or
I was thinking about gluconeogenesis too, but it's in every single answer, so it's dependent on the pyruvate carboxylase.
Yeah, I really think you go, you finish it, and then you come out with you recycle the oxaloacetate, you lose 2 carbons.
Is that
But that just makes me don't you think it's mostly
Is that what does the malic enzyme do?
I think it's malic dehydrogenase it
I just haven't seen
reduces OA. But I'm not sure.
malic acid?
The malic enzyme.
Oh, malic enzyme.
Malic enzyme turns that into malate. We don't need that because we're already doing citric acid.
But you know what? Malate is a byproduct. It is sometimes used to get it out of the cell. In the and you can use malate. Ah, damn! I wish I would remember. I know you can use it instead of.
But malic
I'm undecided between B or C.
What do you mean between those?
A.
yeah, I have that too.
So, okay, you finish the citric acid side, and then you just. Because actually, when you think about it, pyruvate carboxylase is a step of gluconeogenesis. Hey. It makes sense though, if you think about it. Oxaloacetate is the second step here from gluconeogenesis.
I mean, I like before every day, but it's like too simple to
Yeah.
I want to say
Let me-
I'd have
What?
I was thinking look at that.
So the answer that I was A. succinyl-CoA. But my disclaimer down here, we make succinyl-CoA. Continue, we make oxaloacetate. So this is part of the cycle, right? It's not the complete cycle. It's, the cycle is a big circle. Glutamate comes in over here, it goes around. Now you have made an OAA, right? Because you're starting with glutamate. You're not starting from citrate. So you didn't have to use an OAA to make glutamate, right? So glutamate has 4 carbons. You lose one of them as CO2, this one. That's alkyl glutamate dehydrogenase. You get succinyl-CoA. You get from there an OAA. You lose another one by carboxykinase, and then you make it. So that's all you need. Now, actually, so the alternative answer that 5% of you are going to be mad at me about is, so if you did this, so citric acid cycle, you get to malate. Maleic enzyme makes pyruvate. Pyruvate carboxylase makes oxaloacetate. That's sort of an alternative way to get to oxaloacetate. But you don't have to do that. You don't need maleic enzyme to make an oxaloacetate. Yes.
You're talking about economics, like economic.
Yeah. Right.
Wouldn't malate to oxaloacetate, going through that, would that be easier? Going through all of the citric
Well,
acid?
I would say no. I mean, it depends. So, for example, pyruvate carboxylase, you have to use an ATP, right? You don't need any ATPs to get you here. Right? In fact, you can get one here. So, that's the sort of potential advantage of this. Now, you need an NAD here. Well, you get an NADH, which is good too. Because you need the NADH to make the glucose. Yes.
The point of this question is that we're not regenerating oxaloacetate because we didn't start.
That's right, because now we're not doing the complete cycle.
Okay.
And so now the alpha-ketoglutarate is a new alpha-ketoglutarate. It's not one that came from earlier cycle. So the reactions of the cycle, and that has to do partly with the figure that shows all the connections to other pathways, is that you can make these things by starting from other places. You can't, if you start with acetyl-CoA, you're not going to make a citrate, right? A net citrate. Here, you've made a new alpha-ketoglutarate. All right, so here's all right. So here's the thing. So the idea is that this reaction is reversible. So you start here, you go to here, and so you lose a carbon here, but you still have the other 4, right? And that would be true of any of these other entry points. It's potentially a way of, once you've made one of these things, you've made a new one.
Wait, when you said economical, because that's what you said to me earlier, wouldn't it be more economical to go straight to malate and just stop there and then turn into pyruvate?
No, I would say no. Make pyruvate and then make pyruvate back. I would say just make the malate into oxaloacetate. Because if you make the malate into pyruvate, then you got to just make the pyruvate back to oxaloacetate. So it's 2 steps to get from malate to pyruvate to pyruvate to oxaloacetate. Answer B, I mean, if you look at the steps I've listed, well, all right, yeah, I might adjust some things. Those of you who use B, you might be in trouble.
5%.
All right. Hopefully this one will be less than so this one is how are you going to get the pyruvate out to glutamate? And so you have to do so you're millimoles of pyruvate, so a lot of pyruvate. Right? It's the same extract. There's a little bit of OAA, but not very much. So how are you going to make 1 millimole of alkyl glutarate? Alkyl glutarate is 5 carbons, so you need more than 1 pyruvate to make it. All right, so there's some possible answers. Yeah, you can do.
Okay, so this
It's a carboxyl. It's the only thing that makes it. It's only one with the carboxyl, right?
Yeah. Pyruvate dehydrogenase.
I always mess up those two.
It is the one that takes
is that how you get from?
that's how you get acetyl-CoA, the dehydrogenase.
Dehydrated. Okay.
You start
Wait, no.
pyruvate.
Yeah, but it's dehydrated.
Yeah,
That's
yeah, but that's what we want.
But you know what? We don't have an acetyl-CoA. We have to make one, right?
Yeah, from pyruvate. Which is through pyruvate dehydrogenase. Gets you from pyruvate. Like in between.
I think it actually says pyruvate dehydrogenase. Because you know how we don't have any acetyl-CoA. We have citric acid beside it. So we have.
I don't know.
you're using OA.
Okay.
So you're regenerating.
No. It's
I can't even find the. So
I don't know. Then I just won't act like I'm not. Right. What is it now? So why? So what about pyruvate? Why
I can't even find my notes.
What do you think?
We have pyruvate. You have to make first make the acetyl-CoA, right? So you have to take A.
Yeah.
So in order to make 1 millimole you need 1 millimole pyruvate to make enough oxaloacetate so it can combine with 1 millimole acetyl-CoA and then
So we already have the acetyl-CoA?
right, so you use 1 millimole pyruvate to make the acetyl-CoA.
Okay, so that's why you need pyruvate dehydrogenase.
And then you use the other millimole with the malate enzyme to make malate. Malate can become oxaloacetate, which can be fed into the cycle, and then from around the cycle combined with the. There you go.
But do you really need that? Because once you have the but we already have some of the citric acid beside it.
We don't have it now. We don't have like a market. We have Oh yeah, you're right.
So B, because you have to make both.
I was saying, oh, I was saying B because you can also do it with
B. I just thought that he's right. I knew that. I thought he was right because I thought we already have the citric acid side, but that said before that it's so little. So we get this.
B. I think it's B.
Oh,
It's not A or C. Here's the thing. I said CoA. Pyruvate dehydrogenase makes a CoA, makes an acetyl-CoA. So you could make as much as 2 millimoles of acetyl-CoA, right? And then, let's see, what are we trying to get to? Alpha-ketoglutarate. So we need citrate. And once we've got citrate, we can make alpha-ketoglutarate by the subsequent cycle. Right? We've got 2 moles of this. We've only got 1 micromole of this. So this citrate-synthase reaction will work, but this concentration will go way down. Right? So pyruvate dehydrogenase might keep on making acetyl-CoA, but there's going to be nothing for the acetyl-CoA to react with. Right? Now I'm sure you all remember weeks ago, I went through the regulation of glycolysis and gluconeogenesis, and I pointed out that acetyl-CoA activates pyruvate carboxylase. Right? So if the cell is making lots of acetyl-CoA and there's nothing for it to react with, the acetyl-CoA will stimulate some of the pyruvate to be used to make this. And so that will cause more oxaloacetate to be made, which will allow the acetyl-CoA to be converted to cell. And so these two enzymes together will provide enough oxaloacetate to be able to make up the. So the answer, if you want to count up moles, would have to say, let's take one of them, 1 millimole of pyruvate, make it into oxaloacetate using this enzyme. Take the other millimole and make it into acetyl-CoA. Now we've got 1 millimole of this, 1 millimole of that. Put them together, make citrate, and then okay, very good.